SwayamPrabha. Digital India. Educated India.
So, an automated guided vehicle really is a system, it is a vehicle system which is operated with battery power, and it is by and large driverless. So, you have to have a path and a programming associated with such a vehicle, so that you can have the capability of auto unloading and loading between different places, particularly on large assembly lines, etc. So, it belongs really to a class of highly flexible, intelligent and versatile material handling systems used to transport materials from various loading locations to various unloading locations throughout a facility. And particularly in the industrial automation, it is a very important component when we are talking about high volume production. And the whole idea here is that the path planning has to be done in a manner so that there is a sort of a less interaction while movement and more or less parallel flow of material movement along with the AGVs. And not only that, there should be a auto mechanism within the AGV which should be able to avoid collision. So, in a manner, although it is not a complete robotic system, you can say that it is at least a partial robotic system which would have some intelligent capabilities like sensors, etc. built in, and the directives can be given to it through a path which can be laid out either as a fluorescent light path or paint path, or as some kind of a electronic assistance by an underground cable, so that it can help to move the AGV in a particular direction from time to time. So, obviously these automated guided vehicles are becoming a very important and inseparable part of flexible manufacturing system installations these days. So, what are the main components of an AGV? So, obviously the first is the vehicle itself. It is used to move material within the system without human operators or human involvement. You have the guide path, so it guides the vehicle to move along the path which is desirable for it to take. You have to have an onboard control, so there is some kind of a controller which is there, controller unit which monitors and directs system operations, including feedback on moves, inventory and vehicle status, so on and so forth. And there has to be some kind of a overall computer interface which can interact with this whole flexible manufacturing system, and it can automate the process of material delivery and loading and unloading wherever needed. So, such systems are normally mainframe based systems, which is a sort of a host computer, and it plans the delivery of materials falling short at different places along a FMS system. There are several different types of AGVs which are available to meet the different service requirements. They include AGVs towing vehicles, AGVs unit load transporters, pallet trucks, forklift trucks, light load transporters and assembly line vehicles. So, these all form under the category of the automated guided vehicle system. Let us look at the guidance systems in an AGVS. The primary objective of a guidance system in an AGVS is really to keep the vehicle in a pre-designed path or a track, so that the very less interference between two or more vehicles plying parallelly to different stations to meet their material requirements. The main advantage of the AGVS guidance is that the guide path that can be changed easily at low cost compared with the cost of modifying fixed path equipment such as conveyors, chains and tow lines. Moreover, the guide path is flexible, that is crossover of the path is possible and the path does not obstruct other traffic. So, it is all by signal matching or frequency matching that some selection of the path can happen if you have a unit which can recommend a particular frequency or do a local frequency selection on the vehicle unit itself. So, typically there are either wire guided systems or there are optical guided systems. I will probably give you a brief of both. So, in the wire guided systems, an energized wire is embedded in the floor along the AGV guide path. The antenna of the AGV sensors and follows the embedded wire, and wherever there is a path selection issue, you can do it with either a path switch or you can do it with some kind of a frequency identifier. I am going to come into the detail of that just in the next step. The other broad category is the optical guidance, which comes from a colorless fluorescent paint, and there are particles which are painted, which are fluorescent in color, or even taped on the carpeted, tiled or concrete floor. And there are photo sensors on the vehicle which will read and track these colorless particles and process the information signal. The system would permit a clean operating environment this way. You don't need to really get into the additional work of laying out wires wherever the new path needs to be developed with an assembly line, let us say. Otherwise also the systems present are very complex in nature. So typically the optical guidance system is used for most of the time when we are talking about the AGVS systems. There can also be inertial guidance systems. The system has an onboard microprocessor that is used to steer the vehicle on a pre-programmed path. A sonar system is used for obstacle detection and gyroscope for the direction change in this particular case. There can be an infrared. So typically in this category, a sonar sensor is used for performing the obstacle detection. An algorithm, control algorithm is used wherever there is a reflected wave coming out of an obstacle. I would just try to direct the vehicle into a different track. Okay. So therefore there are no obstacle collisions in the process of the movement of the vehicle. There is also a gyroscope which actually tries to sense the different aspects of motion related to the vehicle, on which one can calculate how much distance the vehicle has gone and how it needs to go, so on and so forth. There is also an infrared guidance system, where the system consists of an infrared light transmitters, reflectors mounted on the roof of the facility where this AGVS system needs to be installed. So these reflectors reflect the light, and the radar like detectors relay the reflected light signals to the computer, which then determines the position and direction of travel of the vehicle. So you can program from a control station where the AGV is trying to go or it has to go, so on and so forth. There are laser guidance systems in a similar manner, and in this system a laser beam is used to scan on wall mounted barcoded reflectors. Gives you an idea of the positions they are accurately located earlier. You have a library of such reflectors all around in the facility, so you can actually maneuver based on the readouts of the barcodes and then try to direct the AGV to go toward a specific barcode when you are doing this. Then also there are teaching type guidance systems. In this system a neural network concept is used. A programmed vehicle is actually physically taken by walking through the desired route, and the computer learns about that, and then again programs whenever it is running on a programmed mode. After this teach mode is over, it can actually go through the similar kind of a route as has been planned earlier. It then informs the host computer what it has learned about, and the new path is used for control guidance of the AGV, so on and so forth. So these are the various types of guidance systems which are used in the AGVS. Let us look at how to steer or how to perform steering control, local steering control. So obviously steering control of an AGVS can control the vehicle to negotiate a turn and to maneuver physically in different ways. There are two principal types of steering controls that these AGVS has. One is called the differential speed steer system, and another is the steered wheel control. So let us look at both separately. So in the differential speed steer control, the system uses an amplitude detection type of guidance sensor, and the control is based on balancing of signals from the left and the right side of the sensor. Okay, so that's how. So basically the signals come because of the rotating wheels, wheelbase, from the wheelbase of the AGVS. So it's in the front of the vehicle typically, and so if you have the left and the right signals having a mismatch, obviously there has to be some kind of a steering action so that the AGV is put back into track. Okay, so obviously the differential speed would happen to set in a turn, but if you don't want to turn or you want to avoid the turn, you have to give a reverse signal so that it keeps back on track. That is the whole idea. So whenever a difference exists between the right and left signals, the steering compensates by correcting the steering. Vehicles with differential speed steer controls have less tracking tolerance than vehicles with steered wheel controls. The steered wheel control system uses a phase detection type of guidance sensor to determine whether the vehicle is to the left or right of the path by detecting the positive or negative phase of the sensor signal, and this signal is typically obtained from a guide wire path. So such steering controls actually can be utilized only when there is a particular signal path which is into picture, which is actually a wire path kind of a control. Obviously, if you have an optical signal in place and you have a fluorescent readout, if there is a change in the color coding of the fluorescence, only then this kind of a frequency based selection can be obtained for doing steering control on the AGVS. Let us look at some of the routing systems. So there are two different methods which are used for it. One is called the frequency select method and another is a path switch method. Let us look into both aspects. So this right here is a routing scheme of the AGVS. It is a simple guide path layout which is given here, and this is the frequency select method being incorporated on the guide path layout. So obviously the AGVS has to perform a decision making whenever there is a question of a turn that it needs to be executing. So if there is an AGVS vehicle moving all the way to this junction, at this junction it has to take a decision whether it would try to take left or would go forward in this particular direction. So how do we do that? So consider this simple layout given in A and the frequency select method demonstrated in B. The location where a path splits into two or more than two separate directions is called the decision point, like right about here is a decision point, or maybe here you have another decision point, or probably here another decision point, wherever there is a splitting up into two or more tracks. So at the decision point the vehicle reads a marker which is a passive code device in form of a buried magnet, metal plate or other code devices. So in the floor where multiple frequencies are present to allow the vehicle to go into multiple directions. So the vehicle selects a frequency for the direction it wants to follow. So if supposing I had a different frequency on this end and different frequency here, let us say this is F1 and F2 which are stored on the floor through some kind of a metal plate or some kind of a barcode, So the scanner at this particular position would try to select between this path, whether the path is going to be here or the path is going to be here, by looking at the differential frequencies here and matching with its database in the programmed path what frequency it needs to select for going into the correct path. So that is how you do the frequency select or frequency based select method. The other is a path switch select method. So in the system the guide path is divided into segments that are switched on and off by separate floor controls. You can see here there is a control for this part of the path, and there is another control for this part of the path, and there is some kind of a control switch box which would then be able to cater by switching on different segments of this path. So only one frequency is used in this particular case, so you need not actually get a barcode or some other scanning additional installation in place. So at the decision point the controls are switched on and off depending on the path to be followed, so that the correct tracking of the AGVS can happen at the decision point. So these are the two principal methods of doing the routing, the AGVS routing. Let us also look at some of the types of AGVs. As I had discussed before, you can see schematically how they look like. This is the towing unit, this is the unit load movement unit. You in fact actually see the unit heavy directional unit load movement here in the AGVS scheme. This is a real AGV in an industry which is carrying a unit load. Okay. So there is a fork truck unit, again there is a light load and there is an assembly line unit. These are all different types of units. So the critical issues in the management of AGVS happens to be the guidance systems, the routing, the control systems of the AGV, and then obviously the main purpose, which is the load transfer. What is the capacity of the AGVS to take loads, and then how you can interface with other subsystems like the flexible management system, etc., so that you can actually get the requirement from the subsystem and then put into place so that the material handling happens in the place where it is needed in the right quantity, in the right time, so on and so forth, under the principles of whatever lean manufacturing issues industry has to go through. As regards the control systems, the AGVS have different kinds of control systems. Obviously there is a completely computer controlled system, there is also a remote dispatched control system, and then obviously the manual control system. So computer controlled systems happen to have all transactions and vehicle movements as controlled by a system controller, a main system controller. And basically the idea is that this process controller is going to be giving signals to the guide path, which is this unit right here, and then it also is able to display whatever is going on, and the computation basically as a requirement comes from the host computer. So the planning happens here based on the requirement received from the computer about the various requirements at different stations of the materials. So there is an input terminal, there is a host computer which would do all the computation regarding what material in what quantity at what place, and then obviously the controller would define the flow path in a manner so that the AGV can go to the correct location, so on and so forth. So mostly AGVS systems are more or less in a very high volume production computer controlled. The other mode is a remote dispatch control system. So in this system a human operator is required to issue instructions to the vehicle through a remote controlled station. So this is something which is more semi-human, you can say, but used in situations where the load on the AGVS system for doing material handling is substantially lower. Computer control would be needed when you are planning to have a bulk handling of the materials through the AGVS route. So basically the control system sends the destination instructions directly to the vehicle. So you basically as a human operator plan where the AGV needs to take what kind of load and deliver to what station. And although the human does not have any direct control over the AGVS vehicle, but it can actually plan and say that how much is needed at what station. So that is a remote dispatched control system. And the other one obviously is manually fully controlled. So the operator loads the vehicle and enters a destination into the onboard control panel of the vehicle. Vehicle is routed by itself to the designated destination through the guide path. So it also has to look into the other vehicles and the other traffic which is around for planning its own motion, try to take the shortest path that way. So there is some kind of an algorithmic planning which is involved to do the correct guidance using as less as obstacles on its path with the shortest route. But then again this is a completely manually controlled because the loading unloading has to be done at the operator end. So after reaching the final destination the vehicle stops and waits for the operator to perform a direct unloading. So here the AGVS has to be dispatched back by the concerned assembly line operator or the operator who is waiting for this particular material. So as soon as the material goes to the station he has to dispatch the AGVS back by sending a signal or a switch so that the AGVS can start moving back. So by and large these manually controlled systems are quite simple and least expensive of all the control systems. Some of the industries do employ these kind of systems, particularly in bumper paint shops or other paint applications where there are particular requirements based on the different vehicles which are in place, and also sometimes between bumper paint shops to the assembly line where the bumper is fitted there would be a requirement of quite a number of these manually controlled AGVs. Otherwise in most of the applications where there is a high volume of goods to be planned and delivered, a preference is always for the computer operated or the fully computerized computer controlled AGV systems. So having said that there is obviously going to be an interface of the automated guided vehicle system with the other systems, subsystems which are available. This include automated storage retrieval systems, the ASRS, flexible manufacturing systems. Sometimes there are CNC machines, so they need an interface with these machines. They also need an interface with process control equipment and various other shop floor control systems which are available. So this interface may be a thorough, this maybe either through a distributed data processing network or through a unified host computer which will actually do all the steering and maneuvering based on data from all these different subsystems, but the integration becomes a real challenge at a host computer level. Would also like to learn a little bit about the number of automated guided vehicles which are needed, particularly in a situation to balance the load of deliverance of materials. So let's say let's sort of calculate the minimum number of automated guided vehicles which would be needed if the total average loaded travel distance of the vehicle is given as dd, and the total average empty travel distance is given as dc, and the number of deliveries required per hour is given as ndr based on the demand, and the loading unloading time is given as th, and also the traffic factor that accounts for blocking of vehicles and waiting of vehicles in line at intersections etc. is given as tf. So if there is no congestion, the traffic factor can be considered to be 1. However, if when more than one vehicles are involved, the traffic factor would certainly be less than 1. Normally tf would lie between 0.85 to 1. Okay, that's how you have to plan your system as, or design your system as. So then the, and if supposing we consider v to be the vehicle speed, so then the total delivery time per delivery per vehicle TDV will be given by the sum of loaded travel time and loading and unloading time and the empty travel time as follows. So you have the total time for average loaded travel distance dd to be moved is dd by v, v being the vehicle speed. The total hold time where the loading unloading process happens is th, and then obviously the total empty travel distance is dc, and that divided by v gives the total empty travelling time. So if we suppose that the number of deliveries per vehicle per hour is nd, so if we really wanted to look at the number of deliveries per vehicle per hour, it's sort of frequency of the frequency of trips you can say. And so if supposing TDV is the total time of delivery of a single vehicle, the first aspect that we want to look at is that how the TDV will change if the traffic factor which is basically blocking of vehicles and waiting of vehicles is involved would change. So the TDV obviously will increase because of the intersection or waiting. So therefore you have to divide this real, you have to sort of calculate this time real that it takes in case there is a traffic blockage or obstruction by dividing the TDF with the TF factor. So if the TF is low, supposing there is a low TF value, so obviously the total time needed for the delivery to happen, the real time of the delivery you can say would actually be higher than the total time of delivery that is needed only by looking into the loaded distance, unloaded distance and the loading unloading time summation. So if this were in minutes, so if the number of deliveries per vehicle per hour needs to be computed, it would really be the inverse of this real time. So it's a sort of frequency which can put into place, which we call ND here, which is actually 60 TF by TDV. So basically it is just the inverse of the real time that it would take for doing one delivery. So that's the delivery frequency for one vehicle. And obviously if we had NDR as the number of deliveries required per hour, so this NDR multiplied by the frequency or divided by this frequency, so or maybe just multiplied with the time of the real time of one delivery, which is actually the TDV by 60 TF, which actually give you the number of automated guided vehicles which are needed. Okay. So this is the deliveries per hour, and this is the total time needed for performing one delivery. So one delivery of one vehicle. So this is basically how you calculate the number of or total number of automated guided vehicles which are needed. Let us look at a problem example where Johnson & Johnson is planning to integrate the AGVS and obviously also the automated storage retrieval system, which I will just mention about after this topic, with their FMS system. And JJ is interested in estimating the number of AGVs required to satisfy the need of the manufacturing system. That means the system must be capable of making 51 deliveries per hour. So that is how they are planning, and they have already decided to install a laser guided path system, and unit load AGVS adequately serves the company needs. The following data has been collected. So the vehicle speed data is 180 feet per minute, and the average loaded travel distance per delivery is 540 feet, and the empty travel distance per delivery is 360 feet. We need to, and also the pickup and drop off time have been given to be half a minute each, and the traffic factor is 0.85. So we want to calculate what is the number of vehicles which are needed. So let us first look at the total delivery time. So total time per delivery per vehicle, TDV, is given by the total average loaded time, the total hold time plus the total empty loaded time. In this particular case, the average loaded travel distance is 540 feet at the rate of 180 feet per minute. So many minutes, plus the hold time and pickup time, that is the drop off pickoff time, is about close to 1 minute here, 0.5 plus 0.5, plus the empty travel distance is about 360 at the rate of 180 feet per minute, is about 2 minutes. So you have about 3 plus 1 plus 2 is about close to 6 minutes as the total delivery or total time per delivery per vehicle, and add on the traffic factor to this thing. I mean, the total amount of number of deliveries per vehicle per hour comes out to be 60 TF by TDV, which is 60 times of the traffic factor 0.85 by TDV, which is 6 in this particular case. So it becomes 8.5 number of delivery. So this is the delivery frequency per vehicle per hour, and obviously we need 51 deliveries per hour. So if this were the number of delivery for one vehicle in 1 hour, for a set of 51 deliveries needed, typically 51 by 8.5, about 6 vehicles would be needed to do this job of giving 51 deliveries per hour. Okay, so that is how you calculate the number of AGV vehicles which are needed, number of AGV vehicles needed. So this is a sort of an optimum plan, and there are many other optimization issues like distance criteria, etc., which can come into picture when you have a realistic situation in place. So I think I am kind of done with the topic of automated material handling control. The only other issue which is being left over is the automated storage and retrieval systems, and basically this is a most modern concept, particularly when you are talking about storing of high volume inventory material of lower sizes. So the automated manufacturing systems such as FMS's flexible manufacturing system can provide quick changeovers to different part types and their cost effective production only if we can get the right parts, pellets, fixtures, tools, etc., to the right place at the right time. So for this purpose, their efficient system of storage and retrieval is needed, and by and large, if it can be automated, it is even better. So that is why these ASRS systems come into place. So basically, what are the functions of the storage systems and some of the definitions of the ASRS. So receiving, identification and sorting, dispatching to storage, placing in storage, storage, retrieving from storage, order accumulation, packing, shipping and record keeping for raw materials, purchase parts, work in process, finished products, pallets, fixtures, tools, spare parts, rework and scrap, office supplies and so forth have traditionally been considered to be the function of all these storage systems. And for a particularly an automated storage retrieval system, it typically comprises of the following. One is a series of storage aisles having storage racks, and then also storage and retrieval machines, normally one machine per aisle to store and retrieve the material. One or more pickup and delivery stations where materials are delivered for entry to the system and materials are picked up from the station. This, for example, shows such a delivery point. So you have several bins, as you can locate in this particular regions, as kept as rows and columns, and they are all numbered, and similarly there are different rows and columns on the other side. This itself is the machine which would actually go and retrieve a particular bin from a particular part and bring it, as programmed. So this is how a real ASRS system would look. So typically when you are talking about high level inventory of tools for an assembly line, for example, or let us say pellets and fixtures for a press shop or a die shop or even like a weld shop, so on. So you have to use some of these ASRS systems in place, particularly when the volume of productions are very high volume. So typically the whole ASRS system, as can be seen in the width of this whole ASRS system, is defined as various zones, and there is a certain terminology used for these zones. For example, we have storage space, which actually reflects one such container here, which is basically meant for storing a certain amount, certain part by a certain amount. It is a 3-dimensional space in the storage rack that is normally required to store single load unit of material. There is also a bay. So the bay is somewhere in between here, vertical stack of storage locations from the floor to the ceiling, okay. And obviously there is a row, a series of bays placed side by side. So you can have different rows for one series of bays, as can be looked into here, and then another row, these are all horizontally placed series of bays as rows. We have an aisle unit, which is the space between the two rows for the ASRS machine operation. So typically this is the stacker machine that is in picture, as you saw earlier, and there is a stacker machine at each of these locations, or sometimes even a single stacker, which can go and access some of these rows and columns where a particular unit needs to be carried from, which is otherwise stored in that particular space. So you have an aisle unit, which is the aisle space and racks adjacent to the aisle, this particular unit through which the stacker machine can move. And then you have storage racks, a structural entity comprising storage locations, bays and rows. You can see these are the different storage racks which are into picture, okay. So this is one rack, then this is again a second rack, a storage rack, okay, this third storage rack, fourth, fifth, so on and so forth. And obviously there is a storage structure. A storage structure comprises of storage racks and is used to store inventory items. Usually it is a steel frame structure that is designed to handle the expected size and weight of the stored items. So the infrastructure which is needed to house these bins, these different bins, is basically the storage rack, storage structure. And then obviously you have the storage retrieval machines, the SR machines, move items in and out of the inventory. The SR machine must be capable of vertical as well as horizontal movements, must be able to place and remove the items from storage, as well as interfacing the entry exit points to the ASRS. So that is how you define the ASRS mechanisms. So obviously the terminologies which are used here is basically, one is the storage modules. So the storage modules are used to hold the inventory items. The modules may be pallets, bins, wire baskets, pans and other containers. Typically the principle of design here is to make it as visible as possible, so that the basket can be seen at a glance and it can be planned as to what is falling short, so that it can be replaced. The storage modules must be designed so that they are of standard size, capable of being stored in the structure and moved by the SR machines. So these pallets are very to the dimension. And then there are pickup and deposit stations, so which allow the inventory into the system. It is necessary to have pickup and deposit stations. These are generally located at the end of the aisle, so that they can be accessed by the SR machines from the external material handling system. So this all combined together formulates the ASRS system, as you can see here. There are a lot of additional considerations which go into the design of ASRS systems, which are probably not going to cover in this particular course, but typically a highly automated industrial system would typically have robots at one end, and then there is also a automated material handling system like the AGVS that we discussed in details, and also this automated storage and retrieval systems. These are over and above the conventional chutes or conveyors or rollers or gantry kind of systems which are already in place in most of the industries. So this brings to a completion this particular module of the course on manufacturing systems technology part 2. And typically in this module we in this particular course we covered over and above some of the things which were left over in part 1, like quality and how you can define quality and how you can measure quality by statistical quality control principles. And we also tried to cover some of these automated material handling systems, etc., that the modern day industry envisions to have. Thank you very much for attending this course, and I wish you all the best for your examinations. Thank you.